Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. So in today's lesson, we are going to learn about net ionic reactions. A net ionic reaction is a reaction that only shows the chemical species that actually react with one another. So questions like this double replacement you did, say, in Science 10 isn't really the most accurate way of showing this chemical reaction. Before we go into more detail about net ionic reactions, what I would like you to do is write out and balance this reaction. Remember that if it says it's a solution, it is aqueous. So these are two aqueous solutions that are being mixed together. And because it's two compounds, silver nitrate and sodium chloride, I know that this is a double replacement. So please pause the video now and try to write and balance this chemical reaction. Now that you've had an opportunity to write out the reaction, let's go through how we would do this. The first thing I would do is I look up the ions. So this is silver ion and this is nitrate ion. Over here I have sodium ion and I have chloride ion. So I'll start by making these two compounds. This is a 1-to-1 ratio of positive to negatives, so it nicely comes together as just silver nitrate. Same thing with sodium chloride. It's a 1-to-1 positive and negative ratio, so just NaCl aqueous. Now what I would have to do is I'd have to find a common thing to be replaced. So for instance, I'm going to have the silver replace the sodium because it's positive and sodium is positive, and then they're going to swap out. So double replacement, two things replacing one another. My two products would then be sodium nitrate. Now I know this is aqueous because sodium is soluble with absolutely everything, and so is nitrate. And then I'm also going to have silver and chloride come together, again a 1-to-1 ratio, so nice and easy. But I have to check the solubility of this. Now silver is notoriously insoluble with a lot of stuff, and it is insoluble with chloride, so this is going to be solid, and this would be called a precipitate. Okay, so essentially it's going to form a solid that would sink to the bottom of the beaker. So that's what I'm going to do right now. I'm going to show you what this would look like at the molecular level. So in this first beaker here, I would have silver ions aqueous, and I would nitrate ions aqueous. In this beaker, I would have sodium ions aqueous and chloride ions aqueous. When I mix these things together, what would happen is all of these ions would start to bump into each other. Now, when the silver and chloride ions bump into each other, they are essentially so attracted to one another, they would clump up and they would form a silver chloride ionic crystal lattice, and it would settle down at the bottom of the beaker. So this here would be the silver chloride solid precipitate. So they've undergone a change. They've turned into ions. They've turned into a solid. The sodium and the nitrate are just going to continue to bounce around the beaker. They're just floating around. And essentially, if you look at nitrate here, and you look at sodium here, and you look at them over here, they're really not changing in any way because they aren't. They're just floating around the solution. So we would call the sodium and the nitrate spectator ions because they are not participating in the reaction. They're just observing it. Now, why would we include spectator ions in a chemical reaction? The answer is we shouldn't. They're not doing anything. So I'm going to show you two different types of ways of showing this double replacement reaction. So this is a double replacement reaction. I'm going to show it first as a full ionic, which really shows exactly how everything would appear at the molecular level, and then we're going to change that into a net ionic. So for instance, I don't really have silver nitrate. I have silver ions and I have nitrate ions in solution. They really shouldn't be clumped together because that's literally how they look. Same thing with the sodium and chloride. I don't really have sodium chloride. I have sodium ions and I have chloride ions in solution. Now, when I go to the product side, I still have the sodium ions and I still have the nitrate ions in solution. But I now have silver chloride precipitate, which is solid. That is undergone a change. This has undergone a change. This has undergone a change. The sodium and the nitrate, however, have not really undergone a change, and so they are spectator ions. So the full ionic will help us better understand how to write the net ionic. The net ionic will show everything but the spectator ions, and so I can simply just look and go, all right, this is aqueous here, it's aqueous here. It's really not part of the reaction. I'm going to remove that. This is aqueous here, this is aqueous here. It doesn't change. I'm going to remove that. But the other two, this has gone from being aqueous to solid, and this has gone from aqueous to solid, so it's undergone a change. My net ionic would simply then just be silver ions aqueous plus chloride ions aqueous turning into silver chloride solid. It's net. It only shows what is actually changing. This one is already balanced at 1 to 1 to 1. So again, spectator ions are dissolved ions that are in the reactants and products once the reaction is complete. And a net ionic equation shows the actual chemical change, and they would exclude spectator ions. So now we'll try a couple of questions. We're going to start with a single replacement reaction that's already balanced. And what we're going to do is we'll turn it into a full ionic and a net ionic equation. And then we'll look down here at doing a double replacement, which isn't balanced. So we'll balance it first, and then we will put it into a full ionic and net ionic equation. So the first thing I would do is I would break down everything into what it actually is in terms of being a molecule or an ion in an ionic solution, etc. So for instance, this is a molecule of Cl2. It is Cl2 gas. This is not an ionic compound. It's two nonmetals joined together by a covalent bond. I am not splitting Cl2 apart because it is a molecule. It is molecular. But when I look at this RbBr aqueous, these are two aqueous ions. So I am going to split them apart, and I am going to give them the coefficient of 2 because there are two of each of these. So I have 2 Rb plus aqueous plus 2Br minus aqueous. So what I've done is I've broken down my reactants to make part of my full ionic equation. Then I'm going to do the same thing on the product side. So Br2 gas is a molecule. It is not an ionic compound. This is not an ionic crystal lattice. It is a molecule where two nonmetals, Br and Br, are joined together with a covalent bond. I do not split the Br2 apart from each other because it is not apart from each other. It is literally Br2 gas. Now, when I look at the RbCl aqueous, those are ions in solution, so I do have to split them into two parts, Rb plus and Cl minus. So this would be Rb plus aqueous and Cl minus aqueous. Now again, they have a coefficient of 2, so there's 2 Rb pluses and there's 2 Cl minuses, and I'm going to include that. So there's my full ionic equation. It is showing everything as it is at the molecular level. This is a much better description of this reaction than this single replacement. Now, if I want to do my net ionic, I have to remove any spectator ions. So I'm going to go through each individual thing and see if they are changing. So firstly, I have Cl2 gas, which is a molecule, and this is turning into 2 Cl minus aqueous ions. Well, that's a change. I've gone from being a molecule and I've turned into an ion. This is not a spectator, but an actual participant in the reaction. I am not going to cross out the Cl's. When I look at Rb plus, I've got 2 Rb plus aqueuses on the left, and I got 2 Rb plus aqueuses on the right. They are not changing state. They are not part of the reaction, and Rb plus would end up being called a spectator ion because it hasn't undergone a change. Now, in order for me to make my net ionic, I have to remove my spectator ion from that reaction to make my net reaction. Lastly, I got 2 Br minus aqueous, which is an ion, turning into Br2 gas, which is a molecule. This is a change and it is not a spectator. So I got to leave everything in other than Rb plus in order to make the net reaction. So I have Cl2 gas plus 2 Br minus aqueous turning into Br2 gas plus 2 Cl minus aqueous. Now I need to check to make sure that this is balanced properly. So I've got 2 Cl's here, 2 Cl's here, I got 2 Brs here, 2 Brs here. So that's balanced in terms of number of each type of element. But we are actually going to check it in one other way. We're going to balance using charge. This is something that you do as you continue into more complex chemistry, but it's really easy to explain. What you do is you take the coefficient and you multiply it by the charge on the element to give you the overall charge. So for instance, this is just 1 and there's no charge here, so this has an overall charge of 0. Here on Br, I have 2 times 1 negative, so its charge overall is negative 2. Now, on this side of the equation, the total net charge is negative 2 if I add those things together. So on the other side of the equation, in order for it to be balanced, the overall charge must be negative 2. So let's look at the other side. I've got 1 Br2, it has no charge. 1 times nothing is nothing, so this is an overall charge of 0. And then I have 2 times negative 1, which of course is negative 2. So on this side, we also have a total charge of negative 2. Negative 2 is equal to negative 2, and I know that it's balanced correctly. Moving on to the next one, the double replacement reaction, I'm going to get you to start by just trying to balance this equation exactly the way it is. So the equation is complete, but we just have to balance it. Pause the video and try balancing it now. Okay, now that you've had a chance to try to balance it, let's balance it together. So I notice there's a few things going on here. I have 3 sodiums here, and I only have 1 sodium there. I have 3 bariums here, and I only have 1 barium here. So I'm going to start by saying I need to have 3 bariums on this side, but what that does is it goes 3 times 2 chlorates, which I need now is 6 chlorates. I'm going to go back to the other side. I need to make this a 6 to get those 6 chlorates. But now I have 6 sodiums. So I'm going to come back over here because 2 times 3 is 6 sodiums. 6 times 1 sodium is 6 sodiums. I double check. I now have 2 phosphates. Over here I have 2 phosphates. I have 3 bariums here. And of course I have 3 bariums here. I'm just going to put a 1 in here to emphasize that fact. Okay. The next thing we're going to do is we're going to make a full ionic equation. So I'd like you to pause the video now and try to write out a full ionic equation for this double replacement. Now that you had a chance to try it, let's see how well you did. So starting over here, I have a barium ion. So this is Ba2 plus aqueous, but I can't forget that it has a coefficient of 3. So it's 3 times 1 of these. I have to include that 3 there. I also have chlorate ion, so ClO3 minus aqueous, And I have 3 times 2, so I've got a total of 6 chlorate ions. Continuing on, I got 2 times 3 sodium ions, so I have 6 sodium ions, aqueous, plus 2 times 1 phosphate, 2 PO4, 3 minus aqueous. Now, because there's so much stuff going on here, I'm just going to write my products down below in this space, or I'm going to run out of room. So going on the product side, I've got 1 times 3 bariums, but oh, look, this is a solid. If this is solid, I cannot split these apart. This is a precipitate. I cannot split the ionic compound apart because it sticks together in solution because it is insoluble. So I'm actually going to leave that compound completely together. So I have 1 Ba3 PO4 2 solid. Let's move on to the next one. This is aqueous, so a better description of this compound is actually the 2 ions separated. So I have 6 sodium ions positive aqueous, and I have 6 chlorate ions aqueous. So this would be my full ionic equation because it includes all of the ions, all of the solids, everything involved, exactly how they actually appear at the molecular level. In order to get my net ionic, I have to remove the spectator ions. So what I'd like you to do right now is I'd like you to turn your full ionic equation into a net ionic equation. Pause the video now. All right, now that you've had a chance to do that, let's figure out what are spectators. So here I have barium as an aqueous ion, and then I have barium as a solid. I'm going to leave that alone. It is not a spectator. I have 6 chlorate ions aqueous here. I have 6 chlorate ion aqueous ions here. Those are spectator ions. I am going to remove that from there to make my net reaction. I then have 6 sodium ions aqueous and 6 sodium ions aqueous. They have also not undergone a change. So these are going to be removed and they're not going to be part of my net reaction. The phosphate is an ion to start and then it's part of the solid to end. This does undergo a change. It is not a spectator ion. So when I use my net equation, I'm not going to include the sodiums and I'm not going to include the chlorates, but everything else is going to come down exactly the way it is. I have 3 Ba2 plus aqueous. It's reacting with 2 PO4 3 minus aqueous, and it is turning into 1 Ba3 PO4 2 solid, which is the precipitate. I then need to double check my balancing in 2 ways. The number of atoms, but also the charge. So I've got 3 times 1 barium is 3 bariums. 1 times 3 bariums is 3 bariums. That's good. I've got 2 times 1 phosphate. I've got 1 times 2 phosphate. I got 2 of each. That's great. The next thing we're going to do is we're going to make sure our charge is balanced, and we got to use the coefficients and the charges. So 3 times 2 plus is 6 plus. 2 times 3 minus is 6 minus. So this is a grand total of 0 on the left. Then I've got 1 times no charge. There's no charge written up there. So that's no charge. So this totals 0. 0 is equal to 0, and I know that this has been balanced correctly. So now I'm going to get you to try 2 more questions, but on your own. We're going to do them one at a time. So the first one I want you to do here, I want you to do a single replacement reaction. I want you to do a full ionic. And I also want you to do a net ionic. Pause the video now and give this question a try. Now that you've had an opportunity to do it, let's go through it. I am going to go a little bit faster since we've done quite a few already. First thing I'm going to do is I'm going to split this into 2 ions so I know what I'm dealing with. This is iron 3 plus aqueous, and this is nitrate aqueous because it says it's a solution. And then it says it's reacting with cadmium metal. Now cadmium is CD solid, but what I'm also going to do is I'm going to check out what is cadmium as an ion. As an ion, cadmium is CD2 plus. Now if you're wondering why I'm doing this is allowing me to see what's going to replace with what. This is going to be a single replacement reaction, and so the like things are going to replace one another. The iron is going to replace the cadmium because the cadmium makes a positive ion. So for instance, my single replacement reaction would be Fe bracket NO3 bracket 3 aqueous. I know that this is aqueous again because it says it's a solution, plus cadmium solid. Then the like things are going to replace one another, which means the iron is going to come out of the compound and become a solid, so Fe solid. And the cadmium is going to become an ion and become part of the solution. So this is going to become CD NO3 bracket 2 aqueous. I know it's aqueous because nitrate is soluble with everything. Then I have to balance. I have 3 nitrates here, and I got 2 nitrates here. The lowest common multiple is 6, so I'm going to multiply this by 2 and this by 3 to give me 6 nitrates and 6 nitrates. I then have to turn the cadmium into a 3 to balance out both sides, and the iron as a 2. So there's your single replacement reaction. For my full ionic, I'm going to have to split the ionic solutions into their ions. So I have 2 Fe 3 plus aqueous plus 6 nitrates because I got 2 times 3. So 2 times 3 is going to give me 6 plus 3 cadmium solids are turning into 2 iron solids plus 3 cadmium 2 plus aqueous plus 6 nitrate ions aqueous. So I now have my net reaction. I'm checking to see what I need to cross out. So 2 iron turns into 2 iron solids. I got to keep that. I have 6 nitrate ions aqueous turning into 6 nitrate ions aqueous. I have to get rid of that. That's going to be my spectator. And then I have 3 cadmium solids turning into 3 cadmium ions. Well, that's a change. That has to stay. So my net reaction is going to be 2 Fe3 plus aqueous plus 3 cadmium solids turning into 2 iron solids plus 3 cadmium 2 plus aqueuses. I got to check my balancing. So I got 2 irons, 3 cadmiums, 3 cadmiums. But I also have to check the charge. So I have to make sure that the charge is balanced on both sides. So starting with the iron, it's 2 times 3 is 6 plus. Then I have 3 times nothing is nothing. So the grand total on this side is 6 plus. Then I have 2 times nothing, which is nothing. And then I have 3 times 2 plus. So that's going to give me 6 plus. And so the grand total is going to be 6 plus. 6 plus is equal to 6 plus, and I've got it right. The next one I want you to try here is a double replacement reaction. So I'm going to start with asking you to do a double replacement, then a full ionic, and then a net ionic. So go ahead, give this one a try, pause the video now. Now that you've had a chance to try it, let's see if you got it right. So this is gold 3 plus and nitrate. I know that this is soluble because they have told me it's a solution, but nitrate is soluble with everything. It's reacting with a solution of sodium carbonate. Now sodium is Na plus and carbonate is CO3 2 minus. Now I know that this is soluble because they told me it's a solution, but also sodium is group 1 ion and they're soluble with pretty much everything. So the double replacement would look like this. Gold bracket NO3 bracket 3, because I need 3 nitrates to balance out the gold 3 plus aqueous, plus Na2CO3 aqueous. I need to have a double replacement. I always just like to swap out my positives with one another. So the gold is going to replace the the sodium, and the sodium is going to replace the gold. So now I have sodium nitrate. It's a 1-to-1 ratio. I know that this is aqueous because sodium and nitrate are soluble with everything. And then I have gold 3 carbonate. Now the lowest common multiple of -2 and +3 is going to be 6. So I need 2 golds and I need 3 carbonates. And then I have to check the solubility of gold 3 carbonate. And sure enough, it's a solid. And this is essentially going to be a precipitate. Then I have to make sure my balancing is correct. I have on the left here 3 carbonates and I got 2 golds. So I'm going to balance out the golds first. So I'm going to put a 2 in front of here. That's going to make 2 golds, but at the same time it's going to make 6 nitrates. So I'm going to make my nitrate a 6 on this side, which means I need to make my sodium over here a 6. So I'm going to go 3 times 2 is 6, and that actually solves my problem of the carbonate being a 3. 3 times 1 carbonates is 3. 1 times 3 carbonates is 3, and we're balanced. To do the full ionic, what we need to do is break this down into its ions, if they are ions. So starting over here, I have 2 gold 3 plus ions. And I have 6 nitrate ions. I have 6 sodium ions. And I have 3 carbonate ions. On the product side, this is aqueous, so I've got to split it. So 6 sodium ions aqueous, plus 6 nitrate ions aqueous. And then I have a compound which is solid. So I don't split that apart because it's not split apart. It's insoluble. So then I have 1 AU2 CO3 3 solid. In order to make my net reaction, I have to get rid of the spectators. So let's start by looking here. I've got 2 gold aqueous ions. Now they're part of a solid. I can't get rid of that. I have 6 nitrate ions aqueous, 6 nitrate ions aqueous. That's a spectator. I'm going to get rid of that because it's not changing state. I have 6 sodium ions aqueous, 6 sodium ions aqueous. So that's going to go away. And then I have 3 carbonate ions, which then become 3 carbonate ions in a solid. So that doesn't go away. All I have left to do is take everything that remains, bring it down. 2 gold 3 plus aqueous plus 3 carbonate ions aqueous is turning into 1 AU2 CO3 3 solid. Just need to check my balancing. I got 2 golds on the left. I got 2 golds on the right. I got 3 carbonates on the left. I've got 3 carbonates on the right. I check my charge. 2 times 3 plus is 6 plus. I've got 3 times 2 minus. That's 6 minus for a grand total of 0 on the reactant side. Then I have 1 times nothing. So that's going to be nothing. And so 0 is equal to 0, and I've done it right. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.